Hello and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easier to understand. Today we're tackling another problem regarding turbines, and now that we learned all about how to define states, we are going to solve for the power of the turbine. So under this setup here that I drew with a certain amount of steam coming in, a certain extraction coming out, and the main discharge with all its set properties, what is the power we can extract from this turbine? What is the useful work we can extract from it? So let's read the problem statement to find out what we're looking for. A steam turbine under steady state receives 10 kilograms per second of water vapor at 50 megapascals and 600 degrees Celsius. Steam is partially extracted at 2 kilograms per second in an intermediate stage, where the pressure is 2 megapascals and the temperature is 350 Celsius. In the final discharge section, the pressure and the quality are respectively 75 kilopascals and 95%. Assuming that the turbine is adiabatic, doesn't lose any heat to the environment, and that the variations in kinetic and potential energy are negligible, determine the power of the turbine. Okay, so we are discarding completely kinetic and potential energy. There's no heat being lost to the system, and this is a steady-state system. Okay, so we can apply the continuity equation. And because we have this discharge and extraction system, I actually borrow the same image we used for last time. Okay, so I've written down already the set of properties on each of the states. Let's go ahead and call them state 1, state 2 here on the extraction, and state 3 on the main discharge. So water is coming in, vapor I should say, at 10 kilograms per second into the turbine. Right? It goes into the turbine. It has a high pressure and high temperature. It's going to start spinning this turbine. It's going to do work to this turbine. And as it's going through, we're going to have an extraction section here in which steam at still a very high pressure and high temperature are leaving. Right? And then after the whole thing goes through, we have the main discharge section here in which steam is leaving as a mixture. Right? We can know it's a mixture because it has a quality of 95%, not 75%, of 95%. Okay, so we know it's coming in as a vapor and leaving as a mixture. And then obviously there's work being outputted by the turbine, which is exactly what we're trying to find. What we're going to do, let's apply the continuity equation, that is mass balance, energy balance in the system, so we can find out what is the energy being outputted. Okay, so at the turbine, let's look at the turbine now, and let's draw only the energy that's going into and out of our system being the control volume of the turbine itself. Okay, so we're neglecting neglecting kinetic energy and potential energy. So we have the enthalpy going in from the steam. We have enthalpy coming out from state 2, so H2. We have enthalpy coming out from state 3, and we obviously have the work being outputted, which is W out. Okay. In addition, we have mass. Let's think about the masses that are going in and out of the system. We have a mass flow rate here of 10. Go ahead and put 10 kilograms per second. We have a mass flow rate on the extraction of 2 kilograms per second, and we have a mass flow rate here on state 3, which was not given to us. Okay. If we're applying continuity equation, then that means that the change in the mass flow rate it has to be 0. Right? That is, we're not accumulating water inside this turbine or decreasing the amount of water that is there for the start. All the mass going in is eventually coming out. That's what this is saying, right? So how does this end up being? So this is the things that are going in, that is a 10, minus things going out, that is a 2, and the mass flow rate 3, that has to be equal to 0, which in turn means that the mass flow rate 3 has to be 8 kilograms per second, right? So because there's 10 going in and we only know about the 2 coming out, then the other 8 have to be going out on the main discharge just there. Likewise, we can do the same kind of analysis in terms of energy, right? The energy balance has to be 0. We can't create or destroy. And because there's no potential or kinetic, then we're just talking about the enthalpies and the work being output. So in other words, we're saying that enthalpy 1, which is the only one that's going inside, minus everything else that's leaving, has to be equal to 0. So that is H2, H3, and work out. Note that all of this is in joules or kilojoules, right? Some unit of energy. We're talking about energy just here. But we generally want to know the output in terms of power, because it's just the energy output doesn't really mean much to us. So we want to know the power of the turbine, so we want to know the rate of energy. So what we want to do is we want to take the derivative in respect to time of all these guys. So we could go ahead and derive the whole thing in respect to time. And that's kind of what we're going to do. And the other way we can do that, which is the same thing mathematically, is we can multiply the enthalpies, the uppercase enthalpies, by the mass flow rate, by their respective mass flow rate, that is, times the lowercase enthalpy, and that also gives us a rate, right? Because this is kilograms per second multiplied by kilojoules per kilograms, which ends up being kilojoules per second, which is the same thing as watts or rate. And then obviously on this guy here, we're going to have what we're looking for. So I'm going to rewrite this as mass flow rate of 1, mass flow rate of 2, enthalpy 2, minus mass flow rate of 3, enthalpy 3, minus the work output, but now with a dot to indicate that this is a rate. Okay, so what we're saying here, we can rewrite this and put the work output on the left-hand side. We're saying that 10 times the enthalpy 1 minus 2 times the enthalpy 2 minus 8 times the enthalpy 3 is equal to the work output. Another way to think of this, which is, I think is the best, probably the best way to think of it, is the following. Okay, I think this is the, actually let me highlight this one here. Okay, we can create or destroy energy. So therefore, whatever energy is leaving is originally from our vapor, right? Our high temperature, high pressure vapor, the 15 megapascal 600 vapor. Okay, so the energy leaving through the extraction one, the energy leaving through the main discharge, and the energy leaving in the form of work, they all have the same origin, which is this guy here, because this is the only source of energy that we have in this problem, right? So if we take into account what is coming in, and then we disregard whatever is going out, then that difference there, that difference has to be the energy that we got in the form of power from the turbine. Okay, so let me get rid of all these things here. What do we need to do now? Now that we know that, well, that's quite straightforward, right? If we have this equation here, all we need to find are the enthalpies of state 1, 2, and 3. And mind you that we have information for all the states. We know the first state is at 15 megapascal 600 Celsius. Second one is 2 megapascals 350 Celsius. The third one is at 75 kilopascals and 95% quality. So we have them completely defined. We're good to go. I'm going to actually go ahead and go straight into the superheated steam. Okay, not only because it's quite obvious it's a superheated, but we can also come to our conclusion looking at this one straight off the bat. So I'm looking at, it's 50 megapascal, that's 150 bar, 150 bar. And what you'll see here is that you have the saturated temperature as well. Okay, so the saturated temperature at 15 megapascal is 342. Our temperature is 600, right? So our temperature is 600, which is equal to T1, which is greater than Tsat, which is 342. So therefore, we can be sure this is a superheated fluid. Okay, so we don't have to guess, we can be sure. So I'm looking at 150 and 600. So 600, this guy here. Okay, where these two guys meet is over here, and we're specifically interested in the enthalpy, which is the second guy. So 3581 is our H1. State 2, same thing. Okay, I'm straight onto the superheated steam table. Again, I'm interested in 2 megapascals, so that's going to be 20 bar, so 20 bar. And again, my T sat is 212. My actual temperature is 350. So because 350 is greater than 212, then I can be sure this is a superheated fluid, okay, superheated steam. So I'm interested in 350, this one here. So down the bottom, 350, I'm interested on these values here. And the one that I'm particularly interested in is the enthalpy, which is this fella here. So 3138. That's my second value right there. And the third one, we know it's a mixture, so no point on looking in the superheated table. We need to look in the saturated water and steam. We are at 75 bar, so that's, 75 kilopascals, so that's 0.75 bar. So I'll be looking at this line here. We know it's a mixture, so it's going to have a bit of this guy and a bit of this guy, right? It's going to have a bit of this fella and a bit of this fella. And actually, we know that H3 is a mixture of these two guys, so we can do HF plus the quality and the difference between HG and HF, right? We have all that data, so it's just plug and play, right? Plug our information and find what we're looking for. This is 95% of the difference, and this is the difference here, right? Make it easy for us. So take this, subtract this, you get this middle value here, so 2278, and that gives me my enthalpy 3, which I got to be 2548.1. So 2548.1. So quite straightforward. We have all the states defined. There were no tricks or mysteries in defining these things. It gave us straight off. So now we just need to find what's the power output, which again is just the difference between the original energy that we had available and whatever left the system, right? So whatever left the system. So because we can't destroy energy, whatever, this difference has to be the power output of the turbine. So the output of the turbine will be equal to 10 times H1, which we found to be 3581, minus 2 times, because 2 kilograms per second of the enthalpy 2, which is 3138, minus 8 times of the mixture, which has the smallest energy, and that makes sense, right? 48.1. Okay? Remembering always that to check our units, so we're doing kilograms per second and multiplying that by kilojoules per kilograms. So that gives us kilojoules per second, which is kilowatts. Cool. So I got this to be output to be 9149.2. This is kilowatts, or we can actually go ahead and approximate this to 9.15 megawatts. So that will be our answer there. So the output of this turbine is 9.15 megawatts. And why is that? Well, because we know how much energy we have coming in, and we know how much energy is going out through the extraction and the discharge. So the difference between those guys, because we can destroy that energy, that surplus of energy has to be going somewhere. And because it's the final step of this problem, because this is adiabatic, we know there's no heat involved, then therefore this is leaving in the form of work output from the turbine. Hey, hope you found this useful. If you did, make sure to like the video, subscribe to the channel, and leave any comments that you may have in the comment section so that I can help you out.